class. So lunch will take place during second block class. If you are in an ag class, AE, business, family consumer science, industrial technology, or music, as well as having Mrs. McCarter for art, you will have A lunch. If you are in English, social studies, or special education classroom, you will have B lunch. If you are in ELL, math, study hall, or world language class, you will have C lunch. And if you are in an art class, physical education class, science, or stagecraft or theater class, you will have D lunch. Thanks, everybody.
Now, here's my argument. When I first saw this schedule, because we haven't had any late starts this year, when I first saw they did this with Block 2, I think they made lunch Block 2 because they thought it would be too late if they waited to Block 3. Would you agree with that? I mean, but my thinking was a lot of students probably just got up at like 9:30 and probably ate already. And so you ate at like 9:45 and now you're going to eat at 11. I mean, whatever. Doesn't matter. Okay, so kind of screws up my schedule, but whatever. I guess nobody cares. All right, 18. So it's 17. So 17, it says, how could it be more realistic? Well, we talked there was no wind resistance, air resistance, so that's going to make it kind of unusual. What additional information would be needed? Well, we need to know the effect on wind resistance. Okay, so in C, you go ahead and do your thing there and do it. Okay, so then in 18, they changed it to 100 feet per second, and then you're supposed to plot it and graph it and do all that. Okay, so you would essentially get an equation. You would have x equals 100t instead of 150. And then we would have the same y equals negative 16t squared plus 7, right? Those would be your two equations, right? The only difference is they changed the 150 feet per second it was launched at to 100, okay? And it says plot the result over an appropriate interval, so you can just graph that. Is it a strike? At what speed does it cross a plate? So what did we say we first had to figure out then? Okay, here's the ball. It's coming down, 7 feet high. Here's the plate, 60.5. What do we have to do first? Well, before you find the height, the time that it crosses the plate. Because everything we want to know, is it a strike? What's the speed when it crosses the plate? Those things are all at the plate, which is 60.5. So what we needed to do is set 60.5 equal to 100t. We need to put 60.5 in for x. Okay? And so t equals 0.605. So at 0.605 seconds is when it would cross the plate. And then where do we plug that to see if it's a strike? Well, that's where we need to know the height, right? At this time, we need to know the height. What variable is the height of the ball? That's y. So we need to take that and we need to plug it in there, okay? And according to my notes here, it comes out to be about 1.14. And this is feet, right? So that's pretty low. I would say that's probably not a strike, okay? Is that what you got for number? Anybody? Does that sound right? That number? Okay. And then what's the speed when it crosses a plate? Well, then we need x prime, which is 100. So the x prime is going to always be 100, doesn't matter what time it is. And y prime is negative 32t. So now we got to take that number and we need to plug it in there and we need to put it into x prime squared plus y prime squared, right? So we're going to have 100 squared, and then we're going to have whatever, you put that number in for t, that's your y prime, put that in there, and then do that. And that's the speed at this time, right? And according to my book, it comes out to be 101.86, which shows you the silliness of doing this without wind resistance, right? Because what do you throw it at? 100 feet per second, and when it crossed the plate, it was going faster than when he threw it, right? But, right, so if you don't have wind resistance, it's going to keep going 100 feet per second this way, but then what else is it doing? The gravity's pulling it down. So as the gravity pulls it down, it's speeding it up in that direction, right? So we got 100 feet per second here, and then it's going down, so it's actually going faster when it crosses the plate than when it left its hand. But that's what this equation would say, because we were ignoring wind resistance. So that takes us to number 20. And so when you get to number 20, they say, okay, here's an equation for the x that would include the wind resistance. Okay, so those are there at the bottom of 20, and then that's going to make a difference. But as far as answering the questions, it's very much the same. Now, I'm not going to, again, because of time, we're not going to finish them out to the end, but At what time does it cross the plate? So again, the same thing. You're going to set this equal to 60.5, right? You're going to put a 60.5 in for X, and you're just going to do a solve, okay? According to my book here, that happens at point 442. Okay, hits are quicker, but this is back to 150 feet per second now. Okay, so what time does it cross plate? How much longer does it take than the dragless ball? Well, then you'd have to go back to the question, example 10, and subtract those, so that's fine. So it takes a little longer because the wind is slowing down. At what height does it cross the plate? So we're going to take that and plug that in to there, right? And that'll be the Y value. That'll be the height of it. And they say it's about 3.87. So that's probably a strike. I don't know, 3-4 feet. I don't know. That might be low. You have to know, right? What is the height of the batter? So, is it a strike or not? But so 3.8706 is what they say here. At what speed does it cross the plate? So again, we're going to have to do the derivative of this, right? We're going to have to get X prime. And we're going to have to plug that number into it, and we're going to get Y prime, which we already knew was negative 32t, and we're going to plug that number into that. So we're going to get our X prime, we're going to get our Y prime, and we're going to put it into that. Okay? And then see what speed. And according to the answer book here, it's about 125. They don't do 3 decimal places here, but approximately 125. So it started at 150, so now this is more realistic, okay? So now it is slowed down to 125.9 feet per second. And then D, where does the ball land? What would you do to see where the ball lands? What has to be true when the ball lands? Y has to be 0. So you're going to take 7 minus 16t squared and set that equal to 0, because when it lands, its height is 0, so you're going to put a 0 in for Y and solve that. Okay, you get 2 numbers. One will be negative, which would be back here somewhere, so we won't mess with that, and then that. Okay, and according to the book here, it's about 86.85. Okay, so it's just a matter of this is the horizontal distance of the ball, this is the height or the vertical distance of the ball, and being able to use those equations. The only one they didn't ask is the slope of the path. They could have said at t equals 0.3 back here somewhere, what's the slope of its path, right? And then you'd have just taken your Y prime and divided by your X prime, and that would have given you the slope of the path. That's the only thing we didn't really ask you that. So just be able to use and solve these equations. You use your calculator for all of them. So all you got to know is what does each thing stand for and what are the formulas. Okay? All right. Anything else? We'll come back to that parametric stuff, later and review those things as well. Okay. Let's move on. Get your notes out. Okay. So as you're getting prepared here for this, one of the things we've talked about really since the beginning of talking about derivatives was this idea of a max or a min, and the slope is 0 and stuff like that. And we talked about how, one of the uses could be, you want to make a product and you want to figure out how to maximize your profit. That would make sense. You might be interested in maximizing your profit. Or, of course, the famous snowmobiler stuck in the snow, or the hiker stuck in the snow problem we did, where he wanted to figure out where should he walk exactly to get to the gas station the quickest, the minimum amount of time. What would the minimum be? Now, in algebra class, you can just graph those things. If we have graphing ability, technology, we have an equation, we can graph it, and we can estimate it from that. That's all good. But what we want to know is what's the calculus behind that? How are you finding that maximum? Okay, so we've already done some of that. So now is when we're going to really get into the technical parts of it, and we're going to look at story problems like that, like the snowmobile, right? Or the person stuck in the snow, and we're going to do it, right? Now, what we had to do in that problem, remember, was get it set up, and then we said, and then we'll do some calculus to it to find the minimum amount of time. Well, now we've learned the calculus of how to find that, and we're going to review that and put that all together right now. But remember, I said the hardest part of that was setting up the problem, setting up the equation, and that will probably be the hardest part of this. And so as we spend several days on this, a lot of what we'll talk about is how to get these set up. And the more of them you do, the easier it becomes. You start seeing repeat strategies that you can use on how to set them up. Okay, so let's review what we know about that. So we're talking about global max min now. So we're not using number lines probably most of the time. There is a time you can use a number line to do a global max min, and we'll talk about that. Okay, but when we learned back in chapter 2, and we did a quiz with a problem like this, to do a global max min was when we did our list of candidates. So I've given you an example of a function here. What is the global max of this? What is the highest point on this graph? Or maybe it should, that's not an expression. Let me ask this. What is happening at the highest point? Slope is 0. So this is the F graph. So one place to look for a global max is where the derivative is 0, which of course we know is called a stationary point, right? Where's the lowest point, or what's happening at the lowest point on this graph? Slope isn't 0. Slope is undefined. So two places, and those two together are called critical points. Those two together are called critical points. So a person could say, well, one place to look is at critical points. I don't like calling that one place to look because it's really two places to look, right? And there could be several places a derivative 0, several places a derivative is undefined. But to me, that's two places to look, right? It's critical points, but it's where the derivative is 0, it's where the derivative is undefined. Okay, so doing the derivative is going to be helpful. Now, if I change this function just a tiny bit, now where's the lowest point on this graph? The minimum. And where is it? At the, in this case, left endpoint, right? Or if I included that, it could have been over at this endpoint, right? So it's possible that if this was my function, that the highest and lowest points didn't happen where the derivative was 0 or the derivative was undefined. It actually happened at the endpoint. So we've got to check those. Now, most of our global max min problems are in a closed interval. Most of them are, not always. We might do a max min problem where we don't have endpoints. Well, technically we always have endpoints. Our endpoints might be negative infinity and positive infinity. Okay, now they're not technically endpoints because you can't get to them. But what we might do is, because what you're going to have to do in these problems is you're going to have to show that you have checked all of these scenarios. You're going to have that's going to be your justification as you show. And that's why a list of candidates works, because that's a great way to show you've checked all these things. And whatever value is the highest, this is where, remember, we plug it back into the original function, and whichever one's the highest, that's our max, whichever one's the lowest, that's our min. Now, sometimes if the problem does not give you a closed interval, then what you have to say is, okay, well, here's what the function's doing as x goes to negative infinity, and here's what the function does as x goes to positive infinity. So you just discuss that. So it's kind of a limit. It's kind of like a horizontal asymptote. So you might say you might have a limit situation. Like you might have a graph that goes, see, if we have a graph that does this, and goes up, comes down, and then kind of levels off like so. Well, you find its max, and they don't give you an endpoint, right? Well, the max here is where the derivative max min's here, and then you would say something, and as x goes to infinity, this is approaching, f of x is approaching, say, 2 or something, and here we have a y value of 7, and here we have a negative 5, and so that's our max and min, and we have this horizontal asymptote here. So that would be kind of the same as discussing it. Okay? All right. So that's the idea. And we call this optimization. So optimization, your optimum value. So if you're talking profit, it's pretty obvious. Your optimum would be a max, right? If we're talking cost, you want to maybe minimize your cost, or the guy in the snow. The time, we want the minimum in that case, okay? So we sometimes just talk about optimization or extrema. Sometimes they talk about global extrema, and then that just means both, max and min, right? So one word can take care of two. All right, so let's go through kind of the steps. Now, I'm not usually kind of a recipe kind of guy that I want to just, do this, then do this, then do this. But I found in these problems, it's not a bad idea to make sure you're hitting these steps. Because what happens is you read the story problem and you're just not sure where to go. There's just so much information and stuff. So having kind of a series of steps to follow, I think, is not a bad idea. Okay? So I think the first thing you have to do is identify what you're trying to maximize or minimize. Now, in chapter 2 is easy, because I just said, here's f of x, find the global max and min on this interval. So I already given you the function that you're trying to maximize and minimize. Well, now it might be a story problem where, you got to say, okay, profit. Profit is what I'm trying to maximize. Okay, so that's all step 1 is identify what it is that you're trying to maximize or minimize. And the reason that's important is because then you need to write an equation. So what that does is you say to yourself, okay, I need to find the max profit. Okay, so what I need is a P equals equation. Strangely enough, sometimes for some people the hardest part of this is what do I call the thing that I'm trying to maximize and minimize? Because in chapter 2, I called it for you. I just said f of x equals this. So we were finding the max and min of f. In a story problem, they don't give it to you like that. So you have to write your own. So trying to find the max profit, we're going to write P equals. So that's the equation we're looking for. I want to find the minimum time in the snow, T equals. This is going to be my equation. I don't have to call them those, but it makes sense. Okay? So figuring out a name of what you're going to call it is sometimes a sticking point. Now, we call that our primary equation. And older books used to call it the objective function. Some books call it the primary equation. Whatever. I don't care. Whatever. I'll probably use both terms, or may not just use either, but you might hear that. Okay? Now, we need to get that equation in terms of one variable, because often it's not. Like, for example, let's say we have a cube, or not a cube, but let's say we have a box, and we're trying to find a max volume. Well, you're going to have length times width times height. That's 3 different variables. Right? And we know the derivative is going to get involved because we just talked about that. Our candidates are where the derivative is 0, where the derivative is undefined. So we're going to have to do the derivative with respect to one variable. So we're going to need to get that in terms of one variable. So what we do is we use other information in the problem. And those are called your constraints or your secondary equations, secondary information that's in the problem. If you remember with the guy in the snow, we knew that in the snow he could go a certain distance on the road, or a certain speed. On the road, he could go a certain speed. And we use distance equals rate times time to set up some information. Okay? Now, sometimes, so in chapter 2, when we were doing global max min, we were already on step 3 at the beginning. I gave you the function. It was in terms of one variable. So sometimes, it's pretty quick and easy to get through these first 3 steps. And then sometimes that's the hardest one. Okay? So it just depends on the problem. Because really, once you get past here, then it's just what we learned in chapter 2. Once you have an equation with one variable that you need to find the max and min, well, now you're just back. Now you're just doing this. Now you just got to run through the mechanics of doing it. Okay? So it's not bad. Okay? So, step 4. Find the critical points. Now remember, that means where f prime is 0 and where f prime is undefined. Now, many times we're going to set up fairly nice problems for you that have fairly nice equations. So many times the derivative will not be undefined. Okay? But you have to, in your answer, you will have to somewhere write f prime is never undefined. Right? You have to show that you're hitting all 3 of those. F prime 0, F prime undefined, and endpoints. Somehow you have to show that you're discussing or you've checked all 3 of those scenarios. Okay? All right, so do the derivative, set it equal to 0, see if it's ever undefined, which is usually a 0 in the denominator, typically, is where that's going to happen. Okay? Identify your endpoints or your end behavior. Now, many times that's just given to you. Many times in the problem, it'll just say from here to here. Sometimes you have to think about it, right? Sometimes you have to think about it. Now, sometimes in a real life problem, one endpoint is 0, right? If it's the length of a box, well, what's the smallest the box could be, or the length could be 0. And what's the biggest? Well, that might depend on how much material you have, right? So you might have to figure out what your biggest value is. But that's how you find the endpoints, if they're not given to you. Okay, so you think, what's the smallest that x could be, or whatever your variable is, the smallest x could be, what's the biggest x could be in this problem? And if there really is no endpoint, you can talk about infinity or negative infinity. That's what we mean by end behavior. Okay, and once you've done all those, then you use your list of candidates, or number line, or some justification to identify a max or min. Okay, so let's talk about that a minute. So, if the derivative is 0 a couple places, and it's undefined at one place, and you have a left endpoint and a right endpoint, you got like 5 candidates. We just do a list of candidates. And you plug those back into where? Where do we plug those back into? The original function, the profit equation, the time equation, whatever we're trying to maximize or minimize, whatever we set up earlier. You plug those in. Whichever one's biggest, that's your max. Whichever one's littlest, that's your min. So that's the easiest scenario, and that's what happens a lot of the time. But what happens if you don't have endpoints? Now, some could argue you always have endpoints. So you could argue you could always do a list of candidates. And let's say you just have one candidate, though, that's the derivative is 0 one time. So you can talk about negative infinity, positive infinity, and that one candidate kind of in your list of candidates, and you can figure it out. But what you can also do, if there's no endpoints given, and there's just one place the derivative 0, that's when you could do a number line if there's just one candidate. You could do a number line, and then let's say it went negative to positive on f prime. What does that mean? What do you got? You got a minimum. Well, it's a local min, but we're talking about global min here. It's a global min. Now, why is it a global min? Right, because the number line is just a local argument. It's a local min. To be a global min, it has to be the only candidate, and what you have to say is the word always. So here's how you would do. So if I just had a single, and I didn't want to do the infinity thing with the endpoints, if I had a single candidate, do a number line, and I'd say this function is always negative, or the derivative is always negative before here, and always positive after. So therefore, the function is always decreasing, and then always increasing after. So this is a global minimum. See the difference? So I throw the word always in there, and now I've got a global minimum instead of a local minimum. So that's when you might use a number line. But if you have several candidates, then you would just do your list of candidates, pick the largest, pick the smallest. And then answer the question. Because the question might be how wide should the box be? What's the dimensions of the box? It might be what's the largest volume the box would be. The guy walking in the snow might be how far should he walk on the road? The question might say how far should he walk in the snow? The question might be how much time is it going to take him? What's the minimum time that it'll take him to get there, right? Then you got to answer the question and use your units. All right, so let's work through a few problems. So here's the easiest of all. This would be a chapter 2 type problem. We won't do a lot of these. You might do some here in the beginning on your homework. So let's say we have this function right here. Now, a lot of this will be no calculator, but once we get to the actual quiz, I would say on your homework, try to do as much as you can no calculator, but you get to the point now, I need my calculator. Go and use it. I think when we get to the quiz, it'll probably be all calculated. Because remember, whether you're using the calculator or not, you still have to show these steps, right? It might save you some solving and stuff like that you don't have to show. But otherwise, all the justifications, all those things you have to do. Okay, so we'll try as much as we can with that calculator. All right, so step 1 was identify what you're trying to maximize or minimize. Well, there it is, alphabets, easy. Step 2, get it into, write an equation. Got it. Step 3, get it in terms of one variable. Got it. Right, so all those steps are over. Step 4, find your critical point. So we're going to do f prime of x is 6x squared minus 4x cubed. We're going to set that equal to 0. We're going to take out a 2x squared. We're going to get 3 minus 2x. We're going to get x equals 0, and we're going to get 3 minus 2x equals 0. So 3 equals 2x. I don't want to screw this up because invariably somebody will get 2/3 here instead of 3 halves. Okay, so it's 3 halves. All right, so I got those two candidates. What about f prime undefined? 6x cubed minus 4x squared, ever undefined? Is there ever anything you plug in there and you don't get out an answer? Right? Where's undefined going to be? 0 on the bottom, or maybe a negative in the square root, but usually a negative in the square root, since we always keep the inside the same, a negative in the square root is not in the domain anyway. So negative in the square root is usually not even an issue. Okay, so it's usually a 0 on the bottom. So f prime, never, so I just off to the side somewhere, I'm going to say f prime never undefined. Okay, and I'm just going to circle that so I know I've taken care of it. Okay, I got my stationary points here. So I found my critical points, derivative 0, derivative undefined. Now we got to talk about endpoints. Oh, we're giving them right here. Okay, so that step's easy. So now we're going to go to our list of candidates, and we're going to plug those back in the original. So we're going to do f of -1. We're going to do f of 2. We're going to do f of 0. And of course, we got to make sure these are in our interval, 3 halves or 1.5. And here's where you might want the calculator then, because now we're going to plug those back in the original, especially when you got a number like 3 halves. So why don't you guys do that for me? I'll do these other ones pretty quick here. That'd be -2, that'd be 1, -3, so that's -2, I think. 2 in here, 16, 17. 17 minus 16, that'd be 1. What do we get if we put a 3 halves or 1.5? How much? -8. -8. Okay. Now, we don't do a number line on this one, but if we did, if we had 0, if we had 3 halves, you know, so if you say -1, you say 1, you say 2, put a -1 into here, that's going to be all positive. Put a 1 into here, that's going to be all positive. Put a 2 into here, that's going to be negative. So this goes up, looks like it flattens, a flat spot, and then keeps going up. So we're looking at a graph that's going up, and then it flattens, and then it keeps going up, and then it comes down, right? So up, 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 flat, up, like this. Well, it looks like the max should be there, and sure enough, that's at who? What did I do wrong?
I got 2.68.
For this? Okay.
I clicked it into the
Derivative. There you go. Okay, what do we got? 2.88. 688.
Yeah.
All right. And so there we go. So we got a max here, and it makes sense that our minimum was back here at our left endpoint. Because it went up, 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 then flat, then up some more, and then came back down. And the only question was, did it come back down so it went below here? But it looks like it came back down, back to 1. Didn't go back down far enough to be there. So it looks like our minimum, so then you can just say your minimum is here. Remember, we really just want the y value. Your max is here. Okay, we really just want the y value of that. Okay, so that we did that in chapter 2, right? So that is just kind of review. Basic global max min problem. There's no units attached, there's no real life scenario attached to that or anything like that, right? Okay, so you guys try this one real quick. Okay, now this one, you're going to get to the point, do the derivative. You're not going to be able to solve this. Go ahead and use your calculator. Go ahead and do a calculator solve on this, but you still write out all your derivative. You pretty much do the same amount of work, okay? Maybe just don't show a couple of the solving steps you would have, like where we factored on the last problem, okay? This is where using that vertical bar can come in handy. When we go to do our list of candidates, right? We can just type this in, not with the f of x or anything, just type this, vertical bar, and then x equals, our candidates that we want to plug in, okay? So you don't have to type it in for all those x's each time, especially with 3 or 4 or 5 decimal places, okay? You can also define f of x, do a define f of x equal that, and then you can just type in f of each of those numbers, right? What do you get when you do the derivative equal to 0, when you do a solve, what are you getting there? Anybody got that far yet? 0.367, you agree? Anything else? Is that it? Just one. Okay? Alright? So, let's talk about it from there. Okay, let's talk about it from there. So we do our derivative, we set equals 0, we just get this. So, on the last problem, this stuff in the red wouldn't have had to be there. You could have gotten on your calculator and done a solve right here. And then you could have, and then went right to this. Okay, but all this other stuff would be here. If this calculator problem, right, maybe this stuff in red wouldn't be there, but the rest would have to be there. Now again, you might not, if you did a list of candidates, you don't need the number line. That's unnecessary. That doesn't have to be there. Okay, I just did it to just kind of get a sense of what this graph was doing, but that wouldn't have to be there. Okay, but on this one, this is that scenario I talked about, where we don't have any endpoints given to us, and we only have this one candidate. Okay, now we could do this. So here would be an option. So one option, let's do this in black. So one option would be to now take our number line. Now we're going to have to put in our 0.367 in either option. We're going to, well, I guess we wouldn't, if they want to know the max value, we're going to have to plug it in. So we're going to have to do a 0.367 one way or the other. Okay, but the whole reason you do a list of candidates is so you can compare them and see which one's higher and which one's not. But if you only have one candidate, that doesn't work very well, right? So somebody do that, by the way. Go ahead and put that 0.367. Now, it would be good to do more than just those 3 decimals. You probably should put a few more in. And remember, what you can do is just type in x minus x cubed minus 3x to the 4th, vertical bar, x equals 0.367, whatever all that is. So you can just type it in just like that. Okay, that's how. And then the nice thing about that is you go and grab it, and then you can just delete the 0.367 and you put whatever your other candidates are, right? So if you got 3 or 4 different candidates to plug in, you can just do that real quickly. Okay, doing that right there. Okay, all right. So anyway, let me put the 0.367 on a number line. So this would be the one time where a number line might be something you could do. Okay, so let me put in a 0 here, let me put in a 1 here, I'm going to go back up to my derivative, I put a 0 in there, I get out a 1, so that's positive, I put a 1 in there, I get 1 minus 3, that's negative 2, minus 12, that's negative 14, so that's clearly negative. So what have I got here? I've got a max. Now what was the value here? 0.263. Agree? Anybody getting that? Okay, so we know it's a max, but to finish this now, I would have to say, so if I was going to go the number line route, I would say f prime is always positive before x equals 0.367, and always. Right now, I'm going to not write this out every time, but you may not on your homework either, but you better understand, on the quiz, this, on the gateway, the AP test, the midterm, this would have to be there. Always negative after, so f, remember how we had to always talk about both f prime and f? F is always increasing, then always decreasing. So f of 0.367 is a max. Okay, and again, the key is the word always. Makes it into a global argument not just a local argument. Okay, so that's the black. All right, now, what we could have done, instead of doing that, okay, we could have come over here and we could have said, what about as x approaches infinity? What is f? What is the function f doing? Well, as x, so, right, we just got done doing this. So as x gets really big here, what really matters? The highest power. So what's going to happen as x gets really big? Positive. These are just going to basically go away. And what are you going to end up with? A really big negative. Negative infinity. What about when x goes towards negative infinity? What's going to happen when you raise it to the fourth power? Really big negative, fourth power is still going to be positive. So it's going to be a really big positive, and then the negative 3 is going to make it a really big negative. So again, it's going to go to negative infinity. So right there, that tells me that 0.263 is a max. And you could also argue, you could, without doing the infinity, so on my list, remember that list I gave you, what did we say? We said do a list of candidates, do a number line, or some justification. So in this case, in this particular one, since it's a fourth degree, you could say a fourth degree polynomial is going to kind of look like this. The tails are both going to go down because it's got a negative leading coefficient, the negative 3. So it's a fourth degree polynomial pointing down. So anywhere the slope is 0 is going to be the max. Does that make sense? So because it's that special kind of a graph, you could just discuss that here. Now again, that's not going to work a lot of the time, because a lot of times the equations are going to be more complex than that. Okay? But in this case, it would. So you can do the black with your number line, you can write it as infinity, or you can just discuss what you know about this particular one. So that's why I do this one, just to show you that it could happen where you have that. Okay, where that could be your explanation. Most of the time it's going to look like this. You're going to have a couple different candidates, you're going to do a list of candidates, most of the time it's going to be that. All right, let's look at a real life problem then. This is the type that we're really going to be getting into as we do section 4.3. All right, and I call this the box problem. So you may have seen this in algebra class. So we're going to take a piece of paper, and I haven't drawn this very well. Let's say this is, we'll make it easy. We'll call this 8 inches instead of 8.5. We'll say it's 8 by 11. We're going to take an 8 by 11 piece of paper, and we're going to cut out the corners. We're going to cut out little squares in the corners, right? And we're going to fold those up then. So we're going to fold this up and make a box. Like so, right? So we're going to fold right here along these black dotted lines. We're going to fold along those black dotted lines right there. We're going to fold that up. So these are going to get cut out. Those are going to get cut out. We'll fold those up. We'll have an open face or an open topped box. Okay? So here's the question. The question is, what size squares, and they're going to, all 4 squares will be the same size. What size squares should you cut out to have the box be the max volume? That's the question. What size squares should we cut out so the box is a max volume? Okay? So, step 1 was what? What's step 1? Identify what we're trying to maximize or minimize. What is it? Volume. So that means you need a V equals equation, right? See what I was just saying about how the most confusing thing is how to start? Probably if I would have just let you sit here for a while. I don't know. You might have just sat here for a while and not known what to do, right? So this at least gets you doing something. It gets you saying, okay, we're going to write V equals. We got somewhere to start with this, okay? Because that's step 2, right? Step 2, write an equation for what is to be optimized. Okay, so that's what we need to do. So we need to write a volume equation of this box. Well, what do I need? I need some labels, right? I need some labels of something. So I don't care. What do you want to call this? Now eventually we want to know what size squares should we be. So I would suggest let's label that as X. That's what we're trying to find, right? We're trying to find what size of square should I cut out, okay? So what would this length right here be? That would be this length right here. That'd be 8 minus 2x, right? Because this is x and this is x. So this length here is going to be 8 minus 2x. So right here is going to be 8 minus 2x. Right? And then this side along here is going to be what? That would be this. Well, that's going to be 11 minus 2x. Right? 11 minus 2x over here. And then what's the height of my box? That's just x when I fold those up. Now, you might have started with length times width times height here, right? You might have said, well, the volume of a box is length times width times height, right? So that was step 2. Because step 3 is get it in terms of one variable. Now, if I didn't write out length times width times height, the way we were doing it, we were kind of skipping right to step 3 and getting it in terms of one variable right away. But, so my volume is going to be 8 minus 2x times 11 minus 2x times x. Okay? Now, the calculators will go ahead and do that for us. Go ahead and type that in. I'm kind of curious. Go into your calculator and just type that in. Not the v equals. Don't type the v equals. But just the right side of the equal sign. Just type that in. Now, actually, you don't need to. Right? I don't care. We don't need to write that. Now, it is going to be a cubic, if that matters. You know. But as part of your explanation. But I don't think it needs to. What happens if you just type that in and then hit equals? Does it expand it out? I don't think it does it? It kind of writes it in a factored form still, doesn't it? There's a command under algebra to expand, so you can go expand if that mattered to you, but you don't need to, right? Because we can let the calculator do the derivative of this. That's fine. Matter of fact, let's do it right now, because step 4 was find the critical points now, right? So we need to do v prime. So, or dv dx is what we're doing. So go ahead and do the derivative and type it in just like this. So just do derivative. Now if this x was in front, little word of caution, if this x was in front, you would have to make sure and put that times sign. If you do x parentheses, it doesn't know you're doing times. It thinks that's a function, x up. Now you put x at the end, it probably does think it's times, you're probably okay. But you put 2 parentheses together, it's going to think it's times, but with that letter there, you might want to stick a times sign in there. But anyway, do the derivative of that just the way it is. What's it say? 12x squared. And then we're going to set that equal to 0. Now, is that ever undefined? No. So we say v prime never undefined, because that's just a nice kind of equation, so that's not a problem. So we got that taken care of. So v prime is never undefined. Where's that 0? So now let's go ahead and solve. So again, we're going to let the calculator, you know, we did the gateway test. We want to be able to do derivatives. I get that. But right now, we're after bigger fish, right? I mean, we want to find the global max min. The derivative is one of the steps. So we're going to go ahead and let the calculator a lot of the times do the derivative for us, especially if it's a messy function. We're going to go ahead and just, you can do it, okay? What are we getting? Let's hit control then. Let's get decimal. Okay. The other one's negative, which would be negative. Anybody else getting that?
The second one for me isn't.
So are you getting the 4.82, right?
Yeah.
What's your other one?
1.525.
Okay. That's weird. What you got?
Well, basically.
Okay. All right. So anyway, so we'll go with that. Okay. What? Yeah. Yeah. So. All right. So candidates. Now, what we don't have here is endpoints. So this is what you have to do in kind of a real life situation. Amazingly enough, what some people find as difficult as anything on these problems is finding the endpoints, right? But what you have to ask yourself is, once you identify your single variable that you put it in terms of, you have to ask yourself what's the littlest that could be and what's the biggest that could be. And in this case, we have that. So what's the littlest x we could cut out of here? 0. Now you could argue there wouldn't be any volume. If you don't cut any out, you're not going to have any volume, but that's okay. We'll go ahead and use that as a value. And so we're going to say x could be 0. So that one's not hard. What's the biggest x could be? Isn't it 4? Isn't it 4? Because if you take the shortest side here, if this is 4 and this is 4, there won't be anything left in there, right? I mean, you would meet there, and that would take, and again, you could argue that won't have any volume, but that's what it is. So what's that tell you about this 4.808? Right? We probably don't have to do it. Now, if you did that as a list of candidates and tried to plug in 4.808, I think you'd end up with a negative, right? And of course, you would throw that out then anyway, because you're not going to have a negative volume, right? So my list of candidates, I'm going to do V of 0, I'm going to do V of 4, and I'm going to do V of 1.525, remembering when I plug in the 1.525, I'm probably going to plug in a few more decimal places than that, but you don't have to write out more than that. You just, but you might want to plug in more than that. Your final answer that you give for the problem is the one where you have to make sure you have 3 decimal places correct. Okay, so obviously we plug a 0 into the volume, we can tell right away we're getting 0. We plug a 4 into the volume, we're going to get a 0 on this one, so that's going to give me a 0. Okay, and now 1.525, go ahead and do that. Just anybody get, first person gets it, say it. $60.013. Okay, that's clearly our max. Now, the question would be then, what were the units? And, maybe, so let's assume those were inches. And then what was the question? So if the question was what size square should we cut out, you would say, well, 1.525 inches by 1.525 inches. That would be the dimensions of the squares you cut out. If the question was what's the volume of the largest box you could make, 60.013 cubic inches, right? So you would answer the question. But your justification is all there. We got our endpoints. We can show we checked everything. This could have been one to do a number line. Again, the endpoints weren't given. You could argue that, 0 volume, 0, that's really not a possibility. It doesn't really make a box. So you could do again, this is a cubic, so maybe you could make that argument that it has one place the derivative is 0, or it has 2 places, whatever. I'm not sure you could really make that argument that well. You could, because you're not going to eliminate this one unless you did your endpoint. So probably you're not going to do a number line on this one. You're going to do it with that. Okay? So that's kind of what they'll look like, where you have to be able to get that. You have to be able to get that set up, because the problem on the quiz next week will be you have an 8.5 or you have an 8 by 11 inch piece of paper. You're going to cut a square out of each corner. What dimensions of the square, or what's the largest box? What's the volume of the largest box you can make, or what box would have the largest volume? Period. That's the end of the question. And you go from there, right? So that's why those lists of steps that I gave you, is a good thing to have, I think, to go through. Okay, let's do this one real quick. Just set this one up. We just have enough time to do that. So 2 positive numbers add up to 18. What is the maximum product of those 2 numbers? What is the maximum product of those 2 numbers? Okay. So step 1, identify what it is you're trying to maximize or minimize. What would you say? What are you maximizing or minimizing? Product. So what kind of equation are you going to write in step 2? P equals, I love it, right? See, because that's the hardest part of this problem is what do you call it, right? I think in one of the problems on your homework, they actually give you the equation. They say, what's the max, what is the max of, I can't remember what it is, 3x cubed y squared, and then they tell you about x and y. What's the max of 3x cubed y squared? And the problem is, you're like, well, what do I call it? Well, just call it something. P equals 3x cubed x or y squared. Just you call it something, whatever it is that they're talking about there. Okay, but here we have to come up with it. So P equals. Okay, now it's a product of two numbers. So you could just start by saying, okay, x and y. X and y are my two numbers. So there's my equation. P equals x times y. Okay, product of two numbers. So that's step 2. Step 3 says, got to get it in terms of one variable. So there's some other information in here we can use. Oh, right here. They add up to 18. So what would that look like? X plus y equals 18. That's what we would call a secondary equation or a constrained equation or something like that. So x plus y has got to equal 18, which means y equals 18 minus x. And then bingo, I can substitute that in there. So that's how you do step 3. You have some secondary equation with those variables that you can then substitute in. That's how we got that 11 minus 2x and that 8 minus 2x in the last one. Okay, so now we got x times 18 minus x. Now again, at that point it becomes pretty simplistic because you've got 18x minus x squared. And here's where I still want you to do your derivative and do all that stuff, but when it comes down to the candidate, if you just want to talk about, hey, this is an upside down parabola, because that's what it is. So, but let's go ahead and do it. So step 4 is find your candidates, or your critical points. So that's going to be 18 minus 2x equals 0. So x is going to be 9. P prime is never undefined. We don't forget that. Notice we're going to have that a lot. And that's just because of the functions we pick. But there will be a few that we will do where the derivative is undefined if we have to deal with that. So that's why I made you write this all the time, because I don't ever want you to ever forget it, because then you run across a problem where it matters, and then you forget about it, because you haven't been thinking about it for all these other problems. So at least this time you're always, when you have to write that, you're always thinking about, hey, I got to remember, I got to check that just in case. Okay, so now we're down to our one candidate scenario. So here's where you could say, okay, P is an upside down parabola. It's going to have one place the derivative 0. That's going to be a max, right? You could just kind of write out that sentence and say that. You could do a number line. It'd be a real quick, easy number line you could do here, right? 8, 10, plug into this. Positive, positive. Put it, what did I do wrong here? Oh, I'm looking at P, P prime. So I put an 8 in here, 18 minus 16, yeah, that's positive. Put a 10 in here, 18 minus 20, that's negative. So you could say, okay, it's always increasing before 9, always decreasing after 9, because it's always positive before, always negative after, da-da-da. But anyway, we know that's going to be the max, but what they say, what's the maximum product of the two numbers? So, plug a 9 back into here. So P equals, 9 times 9 is 81. So the maximum product is 81. Maximum product is 81. That's kind of a takeoff on the old kind of geometry problem. If you have a fixed perimeter for a rectangular shape, if you have a fixed perimeter, what shape is always going to give you the max area inside? Square, right? If you have a fixed perimeter and you want to make a cattle pen, right, it's going to be a rectangular shape, and you have a fixed amount of fence, a square is always going to give you the max amount of area. Well, that's really what this problem is. If you look at it, two numbers add up to something, and then what's their max product? It ends up being 9 times 7 to square. Right? Okay. So anyway, we want to go now. Again, somebody else could problem solve this and say, well, just think of all the numbers that add up to 18, right? 2 times 16 is 32. 3 times 15 is 45. 4 times 4, and you could start seeing, and when's your max? 9 times 9 is 81. But so it's a pretty simple problem to use calculus, kind of like a sledgehammer to kill a mosquito kind of thing, right? but it's more about the process is what we're talking about right now, right? Doing the process of using the calculus to do this, okay? All right, 4.3, whatever that next line was on your assignment, it is 4.3, day 1.
He's so bad at doing stuff in the class. He just puts a bunch of stuff at once. Yeah, issuing hard already. Like literally, we could throw down 100 and like, we're only doing this one. We're only doing this one. Like, at the same time. I go get the notification, I get an email. Like, email saying, you have like 15 things added in 30 morning.